Good morning. Today we are going to discuss about the transmission of heat. Heat is a form of energy. It always transfers from high temperature to low temperature. That point we know. Heat transfer from one place to other place by three methods. One is by conduction. Second one, convection. Third one, radiation. So this chapter name is transmission of heat. Total heat we make 7 parts. First one, thermometry, about temperature scale relations. Second one, expansion of solids and liquids. Third one, calorimetry. Fourth one, transmission of heat. Fifth one, thermodynamics. Sixth one, kinetic theory of gases. So total 6 parts of the heat. Okay. In that heat transfers by 3 methods: conduction, convection and radiation. What are the differences between these 3 processes? Heat transfer from one place to other place without movement of the particles is known as without movement of the particles of the medium is called conduction. Example, heat transfer through solids. When a rod is heating, particles not moving but heat transfer from one particle to other particle. That is known as convection. Conduction. Second one, convection. Convection means the heat transfer with the movement of the particles. For example, water is heating, water particles move from one end to other end and heat transfers. Or in the room, if we keep room heater, hot air moving one side, cold air again reach it to that heater and again become hot. Like that air particles are moving. That process is called convection. And radiation means the transmission of heat without any material medium. Without any material medium, heat transfers. That is called radiation. Even the medium is there, temperature of the medium does not rise during the radiation process. Example, heat transfer from sun to earth. Heat transfer from sun to earth. So these are the 3 methods for the transmission of heat: conduction, convection and radiation. For conduction and convection, medium is required. For the radiation, medium is not required. And the radiation is the quickest process of transmission of heat. Radiation is the quickest process. That means the heat transfer with velocity of light, 3 into 10 power 8 meters per second. So that is the radiation. Okay. And for conduction and convection, material medium is required. And for the radiation, medium is not required. For the conduction, particles does not move. For convection, particles move from one end to other end. Okay. Next, steady state. Steady state. One rod is heating. Temperature at this end is theta 1 and one particle taken the heat energy. Then the particle absorbs some part of heat, rises its temperature and the remaining part of heat is given to next particle. Next particle also absorbs some heat, rises its temperature and transfers the remaining heat to the next particle. Like that, heat transfer from one particle to other particles. But after some state, that is called steady state, after reaching steady state, heat absorbed by this particle completely utilized for transmission, not for absorption. Whatever the heat taken by this can give to next one. It will not absorb. So that means the temperatures will not rise. Here temperature theta 1, here temperature theta 2, then whatever the heat they taken completely transfers to the next particles and temperature of the rods cannot increase. That state is called steady state. That state is called steady state. Ends of the rod temperatures remains constant. Ends of the rod temperatures remains constant. Whatever the heat energy given by you can transfer to other end. One end to other end heat can transfer. That state is called steady state. In the steady state, temperature gradient constant. What is the meaning of temperature gradient? Temperature gradient means changing temperature by length is called temperature gradient. d theta by dx. Difference in temperature by length of the rod is known as temperature gradient. d theta by dx is known as temperature gradient. Heat transfer from one end to other end and temperature gradient constant in the steady state. Temperature gradient means d theta by dx, that is Kelvin per meter unit, Kelvin per meter. We have temperature gradient, pressure gradient, velocity gradient, potential gradient. Potential gradient means potential difference by length. Temperature gradient, temperature difference by length. Velocity gradient, change in velocity by length. And pressure gradient, pressure difference by length. So by length is called gradient. Okay, so temperature gradient constant. So now we are going to study about conduction. In the steady state, one rod is there, temperature is theta 1 into theta 2, length of the rod is L, area of cross section is A. Then heat transfers through the rod, heat energy transferring. The amount of heat energy transferring through the rod is directly proportional to area of cross section, directly proportional to temperature difference, directly proportional to time, and inversely proportional to length of the conductor, length of the rod. Heat transfer through a conductor directly proportional to, that means depends on area of cross section. More area, more heat can transfer, and more temperature difference, more heat can transfer, and at more time difference is more heat can transfer, and the thickness of the rod, that means the length of the rod is less, more heat can transfer. So thick walls can transfer more heat compared to the thin walls. So the vessels are made with thick walls only. The vessels are made with thin walls only, because thin walls means more heat can transfer into that vessel. Therefore, by taking all these points, heat transferred proportional to Ka theta 1 minus theta 2 by L. Therefore, Q is equal to Ka theta 1 minus theta 2 into T by L. So this is the formula for transfer of heat through a conductor, where K is known as coefficient of thermal conductivity. Thermal conductivity. With the proportional constant depends on the nature of the material, coefficient of thermal conductivity. K is more, that is good conductor. K is 0, bad conductor. In CCS system, K value is 1 for good conductors, for metals, and K is 0 for bad conductors, that is plastic, wood, etc. Cooker handle is made of a material of bad conductor. So you can hold the cooker hands. cooker handles you can hold with hands because those are made of bad conducting material. But the remaining part of cooker is good conducting material. If you touch it very hot, more heat can transfer to your body, your body can burn. So K is the coefficient of thermal conductivity. K depends on nature of the material. So this is the first formula. Second formula. One is the velocity gradient. Sorry, temperature gradient. Temperature gradient is equal to theta1 minus theta2 by L. Second formula, heat transfer Q is equal to Ka theta1 minus theta2 into T by L. Next, what we require is rate of flow of heat. Heat transferred per second Q by T is equal to Ka theta1 minus theta2 by L. Rate of flow. So rate of flow depends on temperature gradient and area of cross section, and generally area constant. So rate of flow constant in the steady state. In the steady state, rate of flow also constant. So temperature gradient, one formula. Heat transferred, second formula. Third one, rate of flow. Third one, rate of flow. And fourth one, what about the coefficient of thermal conductivity? K. K is equal to, from that formula, QL by A theta1 minus theta2 into T. So K is equal to QL by A theta1 minus theta2 into T. So SI unit is watt by meter Kelvin. Watt by meter Kelvin. How? Energy by time is power. Energy by time is power, that is watt. L by L square, area, so meter, and temperature difference Kelvin. Watt by meter Kelvin. Dimensional formula M1 L1 T power minus 3 K power minus 1. Coefficient of thermal conductivity, dimensional formula. It depends on nature of the material. Coefficient of thermal conductivity depends on the nature of the material. Next, point number 5. There is a rod. There is a rod. It has a thermal resistance, just like electrical resistance. It opposes the flow of heat energy. Thermal resistance directly proportional to length and inversely proportional to area of cross section. Therefore, thermal resistance is equal to 1 by K to L by A. Here also K is the coefficient of thermal conductivity. K is called coefficient of thermal conductivity. Thermal resistance formula L by Ka. L by Ka. What about the thermal resistance units? Thermal resistance units. K means watt by meter Kelvin. So here 1 meter is there. Meter cancel. We are getting Kelvin per watt. Thermal resistance units Kelvin per watt. Thermal resistance units Kelvin by watt. So dimensional formula of thermal resistance is M minus 1 L minus 2 T power 3 K power 1. Thermal resistance dimensional formula is this. Okay. Next, theta 1, theta 2, theta 3, and thickness L1 and L2. Area same. Coefficient of thermal conductivity is K1, K2. Different coefficient of thermal conductivity. Temperatures at the ends are constant. That means steady state. In the steady state, Q by T constant. Then you can write the formula. You can take either 2 or 3 also you can take. Q by T means K1. A same. Area must be same. Ka theta 1 minus theta 2 by L1 is equal to for this rod K2 theta 2 minus theta 3 by L2. In the steady state, you can write like this. From that, theta 2 if you want, you can calculate, or theta 1 minus theta 2 you can calculate. In the steady state, this is one formula. And suppose 3 rods they given like this, but the area should be same. In that case also you can use this formula. You can use the formula. This is K1, this is K2, this is K3. Then K1 temperature is theta 1, theta, theta 2, theta 3. Junction temperature theta. Then K1 theta 1 minus theta by L1 is equal to K2 theta minus theta 2 by L2 plus K3 theta minus theta 3 by L3. Like that you can write. In the steady state, use this formula and this formula. Next, suppose you two rods. Two rods kept in series. They have same area of cross section but different lengths. K1, K2 different materials also area will be same. Then thermal resistance R is equal to R1 plus R2. We know resistance in series, equivalent resistance R is equal to R1 plus R2, and we write the formula 1 by R means 1 by K, equivalent coefficient of thermal conductivity K. 1 by K into length is L1 plus L2 divided by area is equal to this one 1 by K1 L1 by A plus 1 by K2 L2 by A. Area same. Then L1 plus L2 by K is equal to L1 by K1 plus L2 by K2. If the two rods having same length, then 2 by K is equal to 1 by K1, 2 by K. If L1 is equal to L2, 2 by K is equal to 1 by K1 plus 1 by K2. Therefore, K is equal to K1, K2 by K1 plus K2. One important formula when two rods kept in series. If the two rods kept in parallel, they must have same length but different areas. Areas are different, material are different, so K different. Length should be same. So 1 by R is equal to 1 by R1 plus 1 by R2 is the formula. Because the resistance is parallel. Already we learned in 10th standard also. Resistance formula L by length is same na L by Ka. K area A1 plus A2 is equal to K1 A1 by L plus A2 by L. L cancel. Therefore, K is equal to K1 A1 plus K2 A2 divided by A1 plus A2 equivalent coefficient of thermal conductivity when the two rods are in parallel. If areas are equal for the two rods A1, A2 are equal, then K is equal to A cancel, so we get K1 plus K2 by 2. If the two rods of equal length and equal area kept in parallel different material, the equivalent coefficient of thermal conductivity K is equal to K1 plus K2 by 2. So all these points are related to conduction. Next, mercury is a liquid. Even though liquid, heat transfers by conduction. That is a very important point. The mercury heat transfers by conduction method only. Particles of the mercury does not transfer. Next, about convection. In the convection, heat transfers with the movement of the particles. So we explained Newton's law of cooling on this process. Convection example, Newton's law of cooling. And in many places we observe the convection in the room. Heat transfers from heater to the entire room by convection or mosquito jet. Heat after heating, that the mosquitoes and the mosquito smoke will come and transfer from one place to other place. Mosquitoes will die. And trade winds. During seasons, wind flowing from equator to poles and poles to equator, because of temperature differences. At that time, sailing through the oceans can do in olden days business purpose. So that's why trade winds, they are called trade winds. And ocean currents, inside ocean, because of temperature difference, water is flowing from one place to other place. Those are called ocean currents. And the chimney pipe we use in the home to get the smoke out. And exhaust fans we use in kitchen and cinema halls and toilets, because to get hot air. Hot air always stays at the top and it should be pulled out. And cold air enters through the windows and doors. Hot air stays at the top. It should go out through ventilators. All these are examples for convection. And convection again two types: forced convection, free convection. Hot air going by itself, that is called free convection. By force, if we are pulling, that is called forced convection. And what about Newton's law of cooling? Newton's law of cooling. In the Newton's law of cooling, one body is there, temperature theta 1. After dt time, temperature becomes theta 2. Therefore, loss in temperature d theta, the rate of fall of temperature is directly proportional to mean excess temperature of the surroundings. Temperature of the surroundings theta naught directly proportional to mean temperature theta 1 plus theta 2 by 2. Excess temperature of the surroundings means minus theta naught. This is called Newton's law of cooling formula. Therefore, d theta by dt is equal to minus k into theta 1 plus theta 2 by 2 minus theta 1. So, based on this, we have to do the problem. Newton's law of cooling. Next, about radiation. The radiation heat transfers in the form of the waves, and Primos theory. All bodies above 0 Kelvin temperature can emit radiations, and some radiations can absorb also. So it depends on that. Suppose more heat is, more waves are transferring, more radiation transferred, less radiation is absorbed, then that is a hot body. Less radiation is emitting and more radiations are absorbing, that is cold body. So hot bodies, cold bodies can be distinguished based on that. And heat radiation incident on a body. Some part of heat radiation absorbed by this one, some part reflected, some part absorbed, some part transmitted. Therefore, here we have three constant values. One is the coefficient of absorption. Absorption coefficient. Absorption coefficient is the amount of heat energy absorbed by the surface to the amount of heat energy incident. That is called absorption coefficient. Transmission coefficient AD. The amount of heat energy transferred to the amount of heat energy incident on it. The ratio of amount of heat energy transmitted or transferred and amount of heat energy incident is known as the transmission coefficient. And a reflection coefficient RAR. The amount of heat energy reflected to the amount of heat energy incident on it is known as the reflection coefficient. For all the substances, for any substance, A absorption, okay. Actually these are represented like this: lambda absorption, lambda transmission, lambda reflection. For any material, lambda A plus lambda T plus lambda R is equal to 1. Sum of the absorption coefficient, transmission coefficient, reflection coefficient is equal to 1 for any material. For black body means which absorbs all the radiation incident on it is called black body. Suppose some radiation incident on body, completely it absorbs, no reflection, no transmission. That type of body is called black body. For black body, transmission and reflection 0, lambda A is equal to 1 for the black body. Okay. And here we are going to discuss about Stephen's law. Suppose now black body is there, its absolute temperature is capital T, then it is radiating. Amount of heat energy emitted per second through unit area. Amount of heat energy emitted per second through unit area is directly proportional to fourth power of absolute temperature. That is called Stephen's law. Directly proportional to fourth power temperature, absolute temperature. Therefore, Q by TA is equal to sigma into T power 4. It is represented by E. E means not energy. Intensity, energy emitted per second through unit area directly proportional to fourth power of absolute temperature. Sigma is known as Stephen's constant and its value 5.4 into 10 power minus 8 watt per meter square Kelvin power 4. Watt by meter square Kelvin power 4. Okay, so sigma units. And Stephen's constant dimensional formula m1 p power minus 3 k power minus 4. It is also a constant value. Stephen's constant is a constant, not changes for body to body. It is a constant value. Okay. So coefficient of thermal conductivity and Stephen's constant, 2 terms k. Right. Next, Stephen's Boltzmann's law. One more law is there. One body is at temperature of T surrounded by a temperature of T naught. Then T is equal to sigma into T power 4 minus T naught power 4. This is known as Stephen's Boltzmann's law. Stephen's Boltzmann's law. Next, one more.